Sometimes you just need things in order, right? Like lining up books so you know exactly where the third one is, or, well, data in a spreadsheet column. There's something really basic, kind of powerful about having stuff just follow one after another, clearly.
Absolutely. That structure, knowing exactly where something is in the sequence,
Yes.
humans like that. And, well, computers really rely on a very similar idea underneath it all.
And that's exactly what we're digging into today. We're sort of pulling back the curtain on a really core concept in computer science. We're focusing on one specific, crucial section from a technical source we're using, Chapter 4.1, all about arrays from Hello Algo. It's a great resource for algorithms and data structures.
Yeah, it is. And our mission here really is to pull out the key insights about arrays from this chapter. We want you to walk away with this, a solid, really lasting understanding, not just what an array is, but how it works, why it works that way, its main jobs, and crucially why it's both super useful and has some pretty specific limitations. It's about getting that deep feel for it.
Okay, let's jump right in then. Fundamentally, what is an array? How does the source define it?
Well, the core idea is it's a linear data structure. Think of a line, a sequence, a row. But it's a lineup of similar items, like all numbers or all text characters. And the absolute key thing, the bit to really remember, is where they live. They're stored in contiguous spaces in the computer's memory.
Contiguous spaces. Okay, so like seats in a movie theater row, right next to each other, no empty seat in between.
It is exactly like that, packed together, one after the other. And because it's a lineup, each item gets its own specific spot, its own number, which we call the index. The book uses a figure, 4-1, to kind of show this visually. You see the array as one solid block of memory, and the index points you to a specific position within that block.
Got it. So a straight line, identical things, all touching in memory. Each spot has a number. That's the what. So what can you actually do with an array? What are the basic operations?
Right, well, the first thing is just setting it up. Initialization, we call it. The book mentions a couple of main ways. You can create an array of a certain size but without putting values in, yet often they just get filled with zeros or some default. Or you can create it and give it its starting values right away, like, saying 10, 20, 30. The exact way you type it, the syntax, changes between programming languages, but the ID is the same. Reserve that continuous block of memory for a set number of items.
Okay, so you tell the computer, hey, I need space for, say, 5 integers, and it finds a continuous block and reserves it.
Precisely. Now, once it exists, here's where that contiguous memory really shines, accessing elements.
Accessing. You mean like getting the value at spot number 3, or
Yeah.
changing what's in spot number 3?
Yes, exactly. Either reading the value at a specific index or writing a new value to that index. And this is blazingly fast. Think about that contiguous block again. Since every item is the same size and they're all packed together, if you know where the array starts in memory and you know the index number you want, you can instantly calculate the exact memory address of that item.
Ah, so the index works like an offset. If the array starts at memory location X and each item takes up Y amount of space, then item I is just at X plus I times Y. Is that it?
You've nailed it. And that's actually why most programming languages start counting array indices from 0. The element at index 0 is at the start address plus 0 times Y, which is just the start address itself. It makes the math super simple. The index isn't just a label, it's directly used in that address calculation. Figure 4.2 in the book shows this really clearly.
And for the computer, that calculation is just basic math, super quick.
Exactly. It's a constant number of steps. Doesn't matter how big the array is. And that is why arrays give you random access. You can jump straight to any element just by knowing its index and doing that quick calculation. No need to step through from the beginning.
And the time complexity for that is O1, constant time. That's,
Yeah.
wow, it takes the same tiny bit of time to get the millionth element as the first one. That feels like a huge deal.
It absolutely is. It's probably the defining advantage of arrays. But let's flip the coin now. What about when you want to change the structure, like adding or removing things from the middle?
Given they're all packed in tight, I'm guessing that's not going to be O1.
You're right on the money. This is where that contiguous memory becomes, well, a bit of a pain. Let's think about inserting something. Back to those theater seats. If you want to squeeze someone into the middle of a full row, what has to happen?
Everyone from that point on has to shuffle down one seat
Right.
to make room.
Exactly. Same with an array. To insert an element, say at index 3, you have to take the element currently at index 3 and the one at 4 and 5 and so on, and shift all of them one position further down the array to open up that gap at index 3. Figure 4.3 in the book shows this shuffling. And here's a really important consequence the source points out. because arrays usually have a fixed size once created. When you shift everything back to insert, the very last element often just gets pushed off the end and lost. It doesn't automatically make the array bigger.
Whoa, okay. So inserting involves moving potentially a lot of elements, and you might lose data off the end. That sounds inefficient.
It can be, and deleting is kind of the mirror image. If you remove an element from the middle, now you have an empty gap. So everyone after the gap has to shift forward one position to close it up. Figure 4.4 illustrates this, and as the space at the very end, where the last element used to be before the shift, well, it becomes kind of meaningless or holds leftover data.
Okay, so shifting again, but this time forwards to fill the hole. So both inserting and deleting in the middle could mean moving almost the entire rest of the array.
Precisely. And this leads directly to the main drawbacks the book highlights for these operations. First, the time complexity. It's generally high. On average, inserting or deleting is O(n), where n is the number of elements.
O(n), meaning the time it takes grows linearly with the size of the array.
Yes, because in the worst case, like inserting near the beginning, you might have to shift almost all n elements. That's a lot more work than the O(1) access. Second, as we said, there's the potential loss of elements on insertion because of the fixed length. And third, you can have wasted space. If you think you might need up to 1,000 spots, you might create an array of size 1,000. But if you only end up using 50 spots, that memory for the other 950 is still reserved, sitting there unused as part of that contiguous block.
Wow, okay, so it really is a trade-off, isn't it? That contiguous memory gives you this super fast O(1) access, but that same contiguous structure makes modifying the middle, the insertions and deletions, potentially slow O(n) operations. That's a really critical point.
It absolutely is. Understanding that trade-off is key to using arrays effectively. Now, besides adding and removing, there are other basic things, like traversing, which just means visiting every element in the array, usually in order.
Like reading down a list or checking every book on that shelf.
Exactly. And the book shows a couple of common ways to do it in code. You can use a loop that counts through the indices, 0, 1, 2, up to the end, or many languages have a simpler way, like a for each loop, that just gives you each element one by one without you needing to manage the index yourself. Both get the job done.
Okay. And what if you need to find something specific, but you don't know where it is, you don't know its index?
Well, the most basic approach is just to start at the beginning, index 0, and check each element one by one. Is this what I'm looking for? No. Okay, next one. Is this it? And you keep going until you either find it or you reach the end. This process has a common name, linear search. You're just searching in a straight line.
Got it. Simple enough. Now, you mentioned that fixed length issue a few times. What if you genuinely run out of space? Your array is full and you need to add just one more thing. Can you just stretch it?
Yeah, that's the other big consequence of needing that solid, unbroken block of memory. In most standard implementations, the size of an array, once you create it, is fixed. It's immutable. You can't just tell it to be one element longer.
Why not? What if there's empty memory right after it?
There might be, but there might not be. That memory spot right next door could already be in use by some other part of your program. The system can't just override it.
Right. Can't just build an extension onto your house if your neighbor's yard starts right there.
Exactly. So the way you handle needing more space, as the source explains, is actually quite a bit of work. You have to allocate a completely new, bigger block of contiguous memory somewhere else. Then you have to meticulously copy every single element from your original smaller array over into the new larger one.
Oh, wow. So you're not extending, you're moving house entirely, building a bigger house somewhere else and moving everything over.
That's a great analogy. And that copying process, moving elements, that's another O(n) operation. For a really big array, creating a new one and copying everything can take a noticeable amount of time and resources. It's not cheap.
So needing to expand the array is potentially another slow O(n) task. That fixed length thing really bites, doesn't it?
It definitely can. It forces you to either guess the size well up front or accept the cost of this resizing process if you guess wrong.
Okay, I think I'm getting a clear picture. We've covered what it is, the memory layout being key, the operations fast access, slow inserts, deletes, costly expansion. Let's try to boil it down then. What are the headline advantages and limitations, the real pros and cons?
Okay, the advantages all really flow from that contiguous storage of same-sized items. First, space efficiency. Basic arrays are pretty lean. They just store the data itself. Not much extra overhead per item for like pointers or other structural info. Second, the big one, random access. That O(1) time to get any element by its index is huge. And third, something called cache locality. This is a bit more subtle because the elements are physically next to each other in memory. When the computer's processor fetches one element, it often pulls in a small block of nearby memory into its super-fast cache at the same time. This means if you then immediately ask for the next element, like when you're traversing, there's a good chance it's already sitting in that fast cache, making access even quicker.
Oh, interesting. So not only is jumping to any element fast, but walking through them sequentially can also get an extra speed boost because they're neighbors in memory. Cool.
Exactly. Very efficient for reading and iterating. Now, the limitations, which we've really already hit on through the operations. First, inefficient insertion and deletion, especially in the middle. That ON cost due to shifting is the main pain point for modifications. Second, the fixed length. You can't easily resize it. Expansion requires that potentially expensive ON copy operation. And third, the potential for wasted space if you overallocate memory that you don't end up using.
Okay. So, fantastic if you know the size, need fast lookups by position, and mostly read or iterate. But less ideal if you're constantly adding on you moving things in the middle or if the size changes unpredictably.
That sums up the core trade-offs perfectly. Knowing this helps you decide if an array is the right data structure for your specific problem.
Which leads nicely to the last bit. Why does mastering this matter so much? Where do we actually use arrays? What are some typical applications?
Oh, they're absolutely fundamental. You find them everywhere, and they form the basis for a lot of more complex structures and algorithms.
So where might we see them pot up?
Well, obviously, anywhere needing that fast random access, if you need to grab the 50th item in a list right now, an array is great. They're also the workhorse data structure for many standard sorting and searching algorithms. Things like quicksort, merge sort, they usually operate directly on arrays. Even binary search, which is super fast for finding things, requires the data to be in a sorted array first.
Right, makes sense. You need that random access to jump around for sorting and searching efficiently.
Yep. They're also often used as lookup tables. You can use the array index itself as a key. Think about maybe mapping numerical error codes to descriptive text messages. You could have an array of messages, and the error code is the index you use to instantly pull up the right message.
Ah, using the index as a direct map. Clever.
And maybe one of the most significant uses today, machine learning.
Okay.
Arrays are critical here. All those calculations with vectors, matrices, tensors, which are essentially multi-dimensional arrays, are the bread and butter of how neural networks work. The source emphasizes that arrays are really the primary data structure used in all the big machine learning libraries.
Wow, okay. So fundamental to AI and modern data science. That's huge.
Definitely. And finally, they serve as the underlying implementation for many other data structures. Things you might learn about later, like stacks, queues, hash tables, heaps. Often, under the hood, they're actually using an array to store the data. Even representing relationships in graphs can be done with a 2D array called an adjacency matrix.
So understanding arrays isn't just about arrays. It's like learning the alphabet before you can understand words and sentences built from it. It unlocks so much else.
That's a perfect way to put it. It's absolutely foundational.
Okay, well, that feels like a really comprehensive tour of arrays, guided by Chapter 4.1 of Hello Algo. We've seen what they are, those contiguous blocks of similar items accessed by index. We've dug into why that memory layout gives them a one random access, but also leads to the ON cost for insertions, deletions, and resizing. And we've seen just how widely they're used, from basic algorithms right up to machine learning.
Yeah, hopefully this deep dive has really cemented that understanding for you. They might seem simple on the surface, but knowing their strengths, weaknesses, and why they have them is so important.
Absolutely. It really gives you a solid base. And, thinking about those limitations, the fixed size, the pain of inserting in the middle, it kind of makes you wonder, doesn't it? What if you didn't need everything to be right next to each other in memory? Could you design a data structure that maybe sacrifices that O1 random access, but makes insertions and deletions easier? What would that look like?
It's a great question to chew on. What trade-offs would you make if you let go of that contiguous requirement? Something to think about for sure.